Thank you. Thank you everyone for coming. Today we're going to talk about some automatic prompt optimization techniques. And I am Erik. I'm a software engineer with 8 years of experience. I currently work at a San Francisco-based startup called NotDiamond. And the thesis of this company is that there will not be a single model to rule them all, like an AGI that we will use everywhere, but instead there will be like a network of models, each useful for its particular thing, and it will be very important to have like an intelligent infrastructure layer for this network. And that is what we are building at NotDiamond. So whoever has worked with LLMs knows that writing good prompts is very important, and it can meaningfully impact how well your LLM does at the task. So how do we currently approach this problem? So most of the time, people draft an architecture. They hack around like LLM parameters based on like gut instinct. They choose an LLM based on a gut instinct. They work with Claude, they work with OpenAI, and they see which one works best on their problem. They don't really evaluate it though, they just get a feel for it. Then they discover some edge cases that break the app and then manually iterate on these variables. They start changing the format of their prompt. This is a very famous meme I got on Twitter, which is like just pleading with the LLM to respond with JSON. And oftentimes strategies like this work. And that's a little bit unfortunate because it pushes these kind of approaches forward. And then we add manual fixes or manual tips. We try to tell the LLM to like think outside of the box, or please reply only in JSON, only in YAML and stuff like that. Then we launch to production and we discover yet another breaking case, or a case where an LLM does something which we didn't expect or want it to do. And then we again have to go back and reiterate on the variables and go again. And as you can see, this approach is probably not very scalable. And to make matters even worse, at the end, when we are finally somewhere where we believe our prompt is okay, a new model releases and it has another, let's say, personality, and then we have to start again from step one. This happened when GPT-5 released, and a lot of GPT-4 products broke, because the GPT-4 was very agreeable and it was very chatty. However, GPT-5 was much more straightforward, and people's products broke sometimes because of that. And to make the point clearer, each model when it releases also comes with a prompting guideline, and these prompting guidelines can be different from model to model. And when GPT-5 released, it not only came with a prompting guideline, but also with a website where you could input your GPT-4 prompt and it would like try to adapt it to the GPT-5 prompt. So this approach that I just described, it might work for a single task workflow. You might be able to get something working. But, sorry about that. But when we go to multi-stage programs that don't call the LLM once, but call it multiple times. And I have an example here. Let's say we want to do competitor research for our company. We have a prompt which says like, do some competitor research. Then we take the output of that question, of that query, and we say, okay, now take this output and summarize the findings. We have another prompt here. And then we take the summary and we say, now compose bullet point list to send by an email. And as you can imagine, this makes the problem like exponentially harder, because whatever we had problems with in the last point, now we have 3 of those. And these are even harder because while there are like some manual approaches like few-shot learning, so for example, in your prompt, you can input a few examples of your tasks being done correctly. Here, you can't do that anymore because you might have an input and the output, but for intermediary steps, it's much harder to come up with those few-shot learning examples. And the steps depend on each other. So if the first step breaks, then the second step will also break. And it's very hard to debug which step exactly broke. So these are some naive approaches to prompt optimization. The first one, as we talked about already, is manual engineering. It's just iteratively test what works and refine. The second one is few-shot examples. As I said, like we can put some examples of our tasks being performed correctly in the prompt, and this works surprisingly well. However, it's not easy to know which examples to put there, how many examples to put there, and it's not always trivial by how much the LLM gets improved. We can feel it based on usage, but it's not rigorous. The third approach, this is used pretty often, is to rewrite the prompt with an LLM. So you give your prompt, which is, you give your manually written simple prompt to an LLM, and you also give, let's say, the prompting guidelines or some tips, and you tell it, can you rewrite this prompt better? Or, so it can perform better. This is also not ideal because usually this is done without evaluating the prompt afterwards. Many of the AI companies had tools like this, like Claude had one, where you could input a prompt and you would get a better one out, but it wasn't always obvious if the prompt was better or not. And in rare cases, people actually build evaluation sets, actually build like question-answer pairs, and are able to evaluate how well their LLM performs. And yeah, we are definitely going to do that in these examples. So yeah, while we are talking about improving LLM performance, an important thing to take a look at is fine-tuning. Because fine-tuning solves pretty much the exact same problem as we are describing right now. You have a base LLM and you want it to perform better at a particular task. Let's say it's like a customer support chatbot, or you want it to perform math problems better. So you can fine-tune this model. And fine-tuning is basically continuing the learning process of the base model. Of course, there are ways to do this in a more optimal way, like there is like low-rank adaptation fine-tuning where you change fewer weights. You don't necessarily change the entire model weights. But still, even then, this is a very slow process. It requires a humongous amount of data to be trained on, and it's very slow. You need a big GPU to run. One example of this being done is in the earlier days, they used to do reinforcement learning with human feedback, where the LLM would answer, it would give two different answers. The human would do like selection, which one is better, or the LLM would give an answer. The human would rate if it's good or not. This is, of course, not ideal because there is a human in the loop. And what DeepSeek Math did is they had this, there is this family of approaches, reinforcement learning with verifiable results. They had mathematical problems which had like exact solutions, so you didn't need to have a human in the loop. So this maybe makes the problem a little bit easier, and DeepSeek Math worked really well, but it's still, you require a very large amount of data, and you require access to the model. And here is why not just fine-tune, because you need big hardware. It's very expensive both in time and infrastructure, and just in cost. It's very time intensive, and every time your problem changes a little bit, you need to like rerun the training process. You need a huge number of examples, and maybe most importantly, you just can't fine-tune a model that you don't have access to. If you want to fine-tune a closed source model, good luck. There are some methods that they provide an API for you to fine-tune, but you don't know how exactly it's done, and you don't have enough control. And there is one more problem, which is the scalar feedback problem, which I'll talk about in a little bit. So if we compare, in comparison, prompt optimization, for prompt optimization, you have way less assumptions. You don't need model weights. You just need to have a way to call a language model and get an output out of it. So that significantly makes our lives easier. Then you need much less training examples, much fewer training examples. The cost and time is negligible compared to fine-tuning, because you can optimize your prompt with like $10, $5, and with like an hour of your time investment. And you don't need any GPUs, you just need network access, and it's very easy to do on closed source models. And to contextualize this, fine-tuning is doing a search on the weight space of the model, so we are trying to find better weights for the model. And prompt optimization is tuning the prompt, finding a best prompt in the prompt space. So if we try to formalize this problem, we need two things. We need access to a black box language model through an API, any kind of API. And we need an access to a golden data set. So we need access to golden pairs of answer and output, or question and answer, which we will use to guide our model to better prompts. So let's define a few things. So the prompt is what you have. You could say a system prompt, or we have an example here. Let's say we are building an Amazon chatbot, and the prompt would be the part which says, like, you are an Amazon customer chatbot, you have an access to an order history tool, and you have the agency to give $50 refunds, and here is the user message. And then the user message would not be the prompt anymore. That would be the input. So we are trying to optimize this orange text over here. We're trying to find the best orange text to perform best on any kind of user message. And there are some metrics which we can use, which is like exact match, for example. If we are solving a mathematical problem and the answer is 7, then if the LLM says 7, then it's correct. That's exact match, very simple. There is semantic similarity. So if you have a customer support chatbot, it will give you an answer. It doesn't have to be exact, but if the embedding of that answer is similar to the embedding of the correct answer, then you're close enough. There are approaches such as LLM as a judge, where you use another LLM to judge the answer of your original LLM. And there are like deeper LLM as a judge approaches such as faithfulness and relevancy, where you check like how relevant is the answer to the question. And that works by like generating 3 different questions for the answer and then comparing the question embeddings with the original question embedding to see if your answer was actually relevant to the question the user was asking. And there are many, many more metrics that we can use. And if you notice this approach, this looks a lot like a machine learning problem. We have metrics, we have data, and we want to optimize some parameter. So many people thought of coming up with approaches which kind of mimic or are analogies to machine learning methods. And we will talk about 4 of them today. So one of the approaches is called measurable. And how this works is you have the golden set, and this works on multi-step LLM programs as well. If you remember, I said that it's hard to have few-shot examples for the intermediary steps of a multi-step LLM program. So what measurable does, it actually runs your original prompt. So you give it some kind of a prompt, some kind of a simple prompt. It runs your examples, your training set against that prompt, and it traces successful runs. So for the intermediary steps, it saves the input and output pairs, okay, for successful runs. And then it uses those successful runs as a few-shot example to the intermediary steps. So here we solved the intermediary step problem. It also grounds the LLM, and it gives a teacher LLM, which is typically smarter than the LLM that we are going to run on in the end. It gives the teacher LLM the program structure. It says like, this is a program which is used as a customer support chatbot. It requires access to this tool. This tool has these parameters and stuff like this. And then it is also data aware. So it takes a look at your data set and summarizes the data set. It says like, the questions include a format like user name or question and then a message, which is typically about this kind of thing. And it's also demo aware. So it also sees the successful runs. It also sees the bootstrap examples that we have in the previous step. And then we ask this teacher model, based on this grounding, based on the program awareness, data awareness, and demo awareness, to generate an instruction, a new prompt. Okay? And then we actually go ahead and like optimize the hyperparameters, which means we are trying to see which bootstrap examples work best and which instructions perform best. It's like we have a few different instructions based on which, based on if it was program aware or not, if it was data aware or not, and based on which bootstrap examples we used in demo awareness. We have a few different instructions. And we also have a few different sets of bootstrap examples to use in the intermediary steps. So this is like a search. We try to search in this space to check which combination of this performs best. And you can see it in the picture here. It tries to, so in the first step, it bootstraps demonstrations. In the second step, it proposes instruction candidates. And then lastly, it searches different combinations of bootstrap examples and instructions. And there are different ways to do this credit assignment. One way is the greedy method, which is basically changing each step at a time. So instead of optimizing the entire pipeline at once, we focus on one particular step and then try to optimize that one. This is slow, as you can imagine. And according to their paper, it did not result in much better results. There is a surrogate model approach where you have a Bayesian learning model which tries to predict how well the answers will perform before they are actually performed. and that like reduces the space that we need to search. And last is history-based, where we assume that the LLM itself will guess or understand which will perform better based on the history of previous evaluations. Okay, so MIPRO results are presented here. And there are a few different like MIPRO approaches. There's zero-shot MIPRO, there is like a bootstrap, Bayesian bootstrap MIPRO, and these approaches are, like variations of the MIPRO approach. So for example, the zero-shot MIPRO approach is one where we only optimize the instruction. We don't care about the bootstrap examples. You can think of this as tasks which don't really require, which if you give it a good prompt, they don't really require examples or few-shot learning to work fine. And in the inverse of that, Bayesian bootstrap approach is you already have a good prompt. You know you have a good prompt. You just want to find a good few-shot examples to go with it. So that's MIPRO. Okay, so let's go back to the scalar feedback problem. The problem with reinforcement learning approaches and many of the other approaches is that the feedback that we get is scalar. It's like this prompt or this LLM performed against this question, and the performance is like 4 or something, or like this model performed better than this model. And this is scalar reward. And if you imagine reinforcement learning with human feedback, when they take a look at the response, they know why the response is good or bad. But they don't give that feedback to the model. They like say it's good or it's bad, and then the model has to learn based on that one number, which is a not very efficient way if we already know why it's bad or why it's good. So many approaches thought that they should instead give textual feedback to the LLM and try to optimize based on that textual feedback. And just as an example, if you're solving a math problem and you don't get the answer correct, if you ask your instructor and they say, yeah, it's incorrect, that's not very helpful. But if they tell you in step 2 you did this thing wrong, then you can learn faster. So with that in mind, we have another method which is called TextGrad. And this method tries to give an analogy of deep learning approaches. In deep learning, we calculate the gradient of the response for each variable, and then we adjust the variable accordingly to find the minimum point. So in this approach, they define like backpropagation and gradients for LLM chains. And how they do that is they just take the response at the very end, and they ask an LLM, how can this be improved? And you can see this here. So how they calculate this gradient is they say like, here's a conversation with an LLM. They paste the entire conversation, and then they also paste the critique of the next step. So they're backpropagating the feedback. So you can see it here. This response can be improved by something, and then that information is also used to see how this prompt can be improved. And then it just goes back just like in a deep learning approach. And they try to keep their framework very similar to PyTorch, and you can see the similarity here. And the forward pass and backward pass and the optimizer step are exactly the same as in PyTorch. So then based on this differential, we calculate a new prompt. So we say below our criticism on X, and we paste in the criticism that we calculated in the previous step. And then we say incorporating the criticism and produce a new variable, which is a prompt in this case. So yeah, so the TextGrad approach tries to mimic how deep learning is done with textual gradients as an analogy. The next method, which this is a newer method, this came out in July this year, is JEPA, which is a genetic Pareto algorithm to optimize prompts. And this is a multi-objective evolutionary search, and let me explain how the algorithm works. So first, we define a candidate pool, which is just your prompt, your initial prompt. You give it a prompt and an example set, and your prompt is the candidate pool. Then, using an LLM, you ask the LLM to suggest new prompts. And the tree of the prompts will grow as the approach goes on. So this is like a recursive approach. So let me just explain at this stage what happens. Instead of choosing the prompt which performs best on all examples, or that, let's say we have 100 examples, one of the prompts performs well on example 1, just it gets the first example correct and that's it. And another prompt gets all other 99 examples correct, but it gets the first one wrong. So JEPA approach would not throw away the first approach, the first prompt, because the rationale being that prompt got some edge case correct that this other prompt didn't. So from this candidate pool, we run the candidate pool against our golden data set, and we keep all prompts which performed better than all other prompts on at least one task. Okay, so if it performed better than all other prompts on at least one task, we keep it for the next iteration. And then for those prompts that we have kept, so in this particular case, we would keep prompt 3, this one, because it performed task 1 and none other did. And we would keep prompt 2, because it performed task 3 and task 2. But we would throw away prompt 1, because prompt 1 performed task 2, but so did prompt 2. Yeah? Okay, so based on this, we would then ask the LLM, ask a teacher LLM to give feedback on what these prompts did wrong on the tasks that they didn't perform well on. And based on that feedback, we would generate a new prompt, or we do the merging strategy, which is if we have two different prompts which both performed on different tasks, which both performed well on different tasks, we can ask the teacher LLM to generate a new prompt based on the combination of two prompts to cover all edge cases. And after that, we evaluate these new prompts on a mini batch, and if the performance has not improved, we throw it away. If it has improved, then we add it to the candidate pool and continue the process until some budget is spent. So there are a few good things about this. First of all is the Pareto optimal selection. So instead of doing just one, instead of optimizing just the number of tasks we get correct, we optimize for every single task. We want to make sure that most tasks get optimized for. And also another thing is that we get an interpretable evolution tree. So this is just an example of a prompt. That's the original prompt. This was run on the Hotpot QA dataset. This is the example prompt, and this big prompt is the prompt that JEPA came up with. This prompt performs significantly better as the first prompt. And yeah, as I was saying, the resulting prompt tree is interpretable. We can see why everything changed. We can see how, based on what feedback the new prompts were generated. So because the LLM uses a previous prompt plus some feedback to generate a new prompt, we can have these nice feedbacks on how each prompt was iterated upon. And this is a big advantage. And here are the JEPA results. So as you can see, this line is GRPO, which is a fine-tuning approach. And as you can see, JEPA converges much faster than GRPO does. Only in a few steps, it converges to a significantly better result than GRPO ever does. And it performs a little bit better than MiPro as well. And these are not small percentages. Like GRPO, after some huge number of rollouts, gets to around 52%, and GRPO gets to 60%. So that's a significantly better result. And this is the same thing on another data set, and here it's even more striking. The difference is even more striking. And here you can see the JEPA approach compared to GRPO and to MiPro and to baseline, your baseline prompt. And yeah, it's Qwen and GPT models. Okay, so as I was writing this talk, the most recent paper was JEPA. However, after I submitted this talk, a new paper got released. This paper was released this month, and I thought it would be a disservice not to cover it in this talk. So this paper is named Feedback Descent, and here's how it works. It takes your prompt, and it uses a teacher LLM to generate a new prompt, a proposed prompt. And let me see if I'm not missing anything. Okay, so it proposes a new prompt, and then it runs both prompts against a question. And then another LLM verifies which one is better. So this is a really good task for this problem, because this problem works best for problems that are easy to judge but hard to construct. So in this particular problem, we asked the LLM to draw an SVG of a unicorn, which is not a trivial thing to do for an LLM. And then we use a vision model to check which unicorn image looks more like a unicorn. So in this case, this is our, let's say, previous best prompt, or our initial prompt that we gave it, and this is the proposed prompt. It will check which one is better, and if we found a better prompt, great. We just save that as the current best prompt, and we continue iterating forward. If we don't find a better prompt, we tell the LLM, not only tell me which unicorn looks better, but also tell me why. And we take this feedback, and we tell the teacher prompt, the teacher LLM, to generate a new candidate prompt to check against. And the difference of this approach is that these feedbacks accumulate. So if we have a candidate prompt and it doesn't perform well, we get I can show the algorithm. So we have a current best and we have a rational history. So we will generate a new unicorn image, and then we will compare the image with the currently best existing unicorn image. First of all, we'll get which one is correct, and then we'll get the rationale why that one is correct. We will attach the rationale to the rational history, and then if the new prompt is not better, we will just go and continue the loop. And the loop includes the entire history of the rationale. So if the prompt repeatedly can't generate a better unicorn image, it will get more and more feedback over time to be able to actually generate a better unicorn image. And once we actually find a better prompt, then we assign the better prompt to the current best prompt, and we throw away the rational history, because that was used to improve the previous one. Maybe the current one will have other shortcomings, not necessarily the same shortcomings as the previous one did. So unlike previous methods, this evaluator is a comparison, not like a result or feedback on a single item, but it compares two different items. And this method has performed well on a few, but not all of the data sets that JEPA was compared to against this. And you can see some benchmarks here. And let's go to a short demo of a library called DSPy. So DSPy is a library which is built by Stanford, I believe, and it is used to optimize prompts, and it is used to create multi-step LLM programs and try to optimize prompts for them. So I have a small demo here in a Jupyter notebook. So I just import DSPy, and I create the GPT-5 Mini and GPT-5 models. GPT-5 Mini will be used as our model to run against our examples, and GPT-5 will be the teacher model. And let me just zoom in so we can see better. And I have downloaded this math data set, which is just math problems. So we can see I've printed the questions here. So the doctor has told something, and the answer is basically 221. It's an algebra problem. So here is how I make a very simple DSPy module. I just say DSPy.predict question answer. So the framework DSPy, it wants you to program LLMs instead of manually prompting LLMs. So when I say when I do this question answer, under the hood it creates a prompt which types this question and answer. If I'm able to run it, I'll show you in a little bit. And then we can run this on the first example question, and we get an answer back. Yeah. So here I've run an evaluation against all our entire data set to see how well the LLM performs currently before any optimizations are made. And this does not use chain of thought. This uses just a simple one-shot answer. So the LLM either gets the answer immediately correct or doesn't. And against this data set, we have gotten a score of 57.14% right now. And here we are using MiPro optimizer. So we are enabling this optimizer in auto light mode. We have max labeled demonstrations and bootstrap demos at 4. So it can at most have 4 bootstrap examples for each stage. Here we have only 1 stage, however. And then we run this optimizer.compile. We give it the module, we give it the training set, and we also give it the optimizer. Yep. So the optimizer runs, and you can see in the logs here, this is the grounding. So you are giving a single math question, content style, short algebra, return exactly 1 line containing only the final answer in the exact format. So this is trying to come up with a better prompt. And at the end, let's just go ahead and see how it performs. Okay, so and then I've evaluated the optimized module again. So before we optimize the module, and now we have evaluated the module which has been optimized by MePro. And this scores 92.29%, which is like significantly better than our previous 57, I believe. Anyway, and if we inspect the history, we can see, so this is what DSPy generates regardless if we optimize or not. It's like your input fields are question string, your output fields are answer string. All interactions will be structured in the following way with the appropriate values filled in. There is the question, there is the answer. So it like makes it so your approach is like more rigorous instead of like just you prompting the LLM in any way you want. But the magical part of this is what MePro generated, which is this part. So this is the instruction that MePro actually generated. And it says like, reason about the problem internally, do not produce chain of thought. I don't even really know what that means. How can it reason internally? And then it gave it some more information about the input handling, the computation rules, and the output formatting. It says it's strict, maybe because sometimes the LLM would not just output a number. And it says like normalize the answers. And return exactly 1 short answer and nothing else. And here you can see the examples. So this is the bootstrap examples that I was talking about. This is now embedded in the prompt. So the prompt sees these examples. And it can few-shot learn from these examples and produce a better answer. And then it passes the user message, and here's the answer that we get back. And with this approach, with just doing a MePro optimization, we got a significantly better result than without it. And you can use the SPy to optimize with JEPA as well. TextGrad has a separate framework. And yeah, I think that's it. Thank you. And I would love to hear questions if you have any questions. Yep. I think you have to wait for the microphone, sorry.
Yeah, I have a question right away. Can we find this notebook somewhere in GitHub, probably?
I will upload it to GitHub, yes.
Yeah, okay.
Yeah, not right now, but I will upload it and share it.
Thank you.
Yeah. Also, this was one of the example runs from DSPy documentation, so you will be able to find it there as well, but I can upload it.
Okay, one more question. What about JEPA optimizer for the SPy framework? It's currently in development stage.
No, JEPA exists right now. You can use JEPA.
When we compare JEPA and MePro v2, how much resources take when compared with these 2 kinds of optimization?
Right. So JEPA will definitely be a little bit slower. Because there is more inherent like LLM calls, because you are asking the LLM for a feedback every time. However, compared to like how long you are going to run the prompt for in inference time, in many cases it would make sense to make that upfront.
Yes, it depends on LLM. But actually, if we don't have enough data sets, when we cannot predict the answer. For example, math data sets here, it's have only one answer, and this can be. But how we can try to prepare data sets from, for example, from books. I mean, not the math, not the physics. I mean something like scientific, sci-fi, maybe something like drama. So when we try to, how to create data sets to improve prompts for generate much more creative texts.
Yeah, that's a really hard question to answer, I think, because like data collection is one of the bigger problems, I guess. You would need to either come up with the examples manually, or depending on what product you build. Let's say you build a customer support chatbot and you have implicit or explicit feedback about your customer support. You can check like how did the customer support human answer the questions correctly, and then use that as data. I don't know how you would be able to do that same thing with science fiction writings, but yeah, something of that sort. You would need to collect the data, and it's nice that these approaches can work with significantly less data than fine-tuning. And actually, like some of these approaches can work with as little as like 20, 25, maybe like 50 question-answer pairs, which is not that much, but. And also, there is another interesting thing that most of these approaches split the training and test sets in reverse. So in machine learning approaches, you would usually use 80% of your data set as train and 20% as test. But for example, in MiPro, you would typically use 20% as train and 80% as test, because it's easy to, it's much more important to validate that your results work correctly. They just found that this approach works better. So it could work with a small amount of data. Yeah, maybe you wouldn't be able to validate it well, but
maybe we can try extract something from the just a raw book texts.
Maybe
Something like graphs, something like okay, it's paragraph is the best. Okay.
Maybe, yeah. Thank you. Any other questions?
Yes, thank you for the interesting presentation. So one of my questions is always, as I read papers, what daily practices can I extract from the science? So, for example, what can you suggest after hearing this? What daily best prompt techniques or agentic work-wise kind of some workflow can we extract from this?
Yeah, that's a great question. I think many people, when they saw like that LLMs can perform better with better prompts, many people tried to push this idea that prompt engineering is the future and now everybody needs to be a prompt engineer. So I think that's probably not entirely true, and probably we should use computers to come up with better prompts than we can. Maybe it's good to brush up your communication skills to like talk to your cursor ID or whatever, but you don't necessarily want to write business critical prompts by hand. And I think one thing that you could take day to day is evaluate how well your prompts work and try to use some automated approaches to get better prompts, such as these approaches, or some companies which solve the problem, like NotDiamond or others. And yeah, I would say like if you have a multi-step LLM program and it's not trivial, you can probably gain meaningful advantage if you optimize in an automated way.
Maybe I can elaborate on that. Basically, what we can do is maybe to try to process the multiple outputs of one of the same prompt and maybe get the better answer and then enforce the answers, because kind of that I heard here that you kind of have some kind of choices and the discriminator chooses the best one.
What you're describing is not similar to this, because what you're describing happens at inference time. So you right. Send the same question to, let's say, multiple LLMs or to the same LLM. But what happens here is it at build time, at develop time. So in here you are trying to get the best prompt, and then later on you just use that best prompt. And you wouldn't need to run it multiple times.
Okay, thank you.
Any other questions?
If you don't have any more questions, you can just join this communication around the piece of pizza. And, yeah, network there. So,
thank you. Thank you for coming. Huh?